finish up this discussion of neural networks, I'd like to talk about a few practicalities of how to use them and particular tricks that people have developed for training them. Neural networks are often very big, with an enormously large number of parameters, and they have a huge capacity for learning and memorization. As a result, they can be prone to overfitting unless you've got an enormous amount of data to throw at them, and therefore regularization can be very important. There are a number of ways in which to approach this. The same classic weight norm-based regularizations that we've talked about before, those can be applied to neural networks too, and this can work quite well. Both L1 and L2 regularization penalties are commonly used. L2 regularization in neural networks is often termed weight decay. The way that the penalty term winds up affecting the weights can be separated out from the other loss gradient and handled in a kind of direct pre-processing step, just downscaling the weights before then applying the proper gradient update. This makes it relatively easy to implement kind of quasi-independently from the loss function proper. Another pretty effective regularization technique for neural networks is known as dropout. This effectively switches off a random subset of the neurons in the network at every sample update. So if you're processing batches or mini batches, the configuration of available neurons changes for each sample in the mini batch, not for the mini batch as a whole. In practice, this is implemented by multiplying element-wise with a matrix randomly populated with zeros and ones. During the backpropagation, the gradients are averaged over the whole mini batch, and so even if some neurons were off for some of the samples in the mini batch, they will still get gradient updates from the averaged version. Doing neuron by neuron dropout doesn't make sense for convolutional layers, but there's a kind of convolution-specific equivalent that instead switches off individual convolutional filters. So dropout might seem like a kind of weird thing to do, but it can be understood as something similar to bootstrap aggregation, which we saw with random forests. Each of the samples in your mini batch sees a different set of neurons on. In effect, it's being processed by a different network. When you average over all of the samples, you're aggregating over all these different network topologies, and that gives you an improved response. Dropout also prevents the network from relying too heavily on any individual neuron because it doesn't know whether or not it will be active at any given time. This can help with generalization and also just the robustness of the network results. When it comes to test time for a network that's been using dropout, obviously you leave all of the neurons on all the time. There is no random dropping out at test time. However, you have to compensate for the fact that during training, half the neurons, or however many, were always off. And so the way that you do that is by downscaling all of the activations in proportion to how many neurons were off at any step of the training. In this way, the decision processes of the network see similar scale of responses as they did at any training step, although with a greater variation because more neurons are on. Yet another related and in some ways complementary technique is known as batch normalization. So learning in a multi-layer neural network depends on the inputs to each layer and to the distribution of inputs that each layer sees. But also, it's receiving its inputs from previous layers which are being trained too, and so their output distributions will be changing. So each layer is trying to hit a moving target. The inventors of batch normalization use the term internal covariate shift to denote this shifting around of the data distributions, output and inputting from each layer during training. Batch normalization attempts to mitigate this by rescaling and offsetting the outputs from each layer for each mini batch. So the statistics, the mean and variance of each data point in each layer is calculated over the mini batch for each mini batch process, and then those values are used to rescale the inputs so that they have a consistent distribution. The exact values of the mean and variance that will be imposed for each dimension are learned as part of the batch normalization process alongside the training of the model. Batch normalization has been shown to speed up learning significantly and also to enable learning in circumstances where previously it was difficult to get convergence. It helps to reduce the dependence on careful initialization of the weights at the start of training, because the activations are constantly being rescaled into a reasonable value rather than just exploding or collapsing. It also has a regularizing effect. So the particular details of each sample as it's passing through the network will be modulated according to all of the other samples in the same mini batch as it. Assuming that the data is shuffled between epochs, then each time the model sees a piece of data, it will be seeing it in amongst a bunch of other different pieces of data, and so the values that it sees for it will be a bit different. This can help avoid getting too hung up on the specifics of individual data items. A downside of batch normalization is that it significantly increases the number of parameters in the model because you have to learn these individual statistics for every weight. So at test time, these statistics are replaced by global average values which have been determined from the entire training set. Deep networks are extremely data hungry. It takes a very large amount of data to constrain the enormous number of parameters that need to be learned. But data can be scarce or at least very expensive to generate, and so we would like to find ways of getting more out of what we have. One common approach is called data augmentation, which takes the training data that you have and increases it by applying various kinds of perturbation to it to generate new samples which are similar to the old samples but different in some way. This is commonly applied to images, for example, by doing rotations and flips, by adding noise and applying color shifts or blurring. This kind of data expansion has been used very successfully with lots of image training models and for things like object detection in videos. Data augmentation also has a regularizing effect because it smears out all of the individual data samples into a population of relatively similar ones, deterring the network from getting too hung up on particular specifics like the noise properties of any individual image. What we think of as the more important structural properties of the image, things like catness in an image of a cat, those will survive the perturbations and be more likely to be picked out as consistently significant. As mentioned in the discussion of convolutional neural networks in Lecture 6.2, there are an awful lot of commonalities across images, lots of structural features that are pretty consistent or at least are frequently occurring across images from different sources. And we know that, for example, CNNs will often tend to converge on detectors for many of these sorts of features. Similar commonalities also occur in other data types, for example, text and sound. By this point in the story of deep learning, many people have created and trained and tested extensively very large, very performant models which have been trained with enormous data sets for large periods of time at great computational expense, and many of these models are available to you just by downloading from the internet. These models have been trained on standard tasks like classification of ImageNet, and typically these are not the kinds of tasks that we actually want to perform. However, they will have some commonalities with those other tasks, and the models that have been trained for ImageNet classification, for example, will embody an awful lot of knowledge about images in general and lots of universal properties that are very useful for lots of imaging tasks, as well as the specifics required for identifying the 1000 classes in ImageNet. So we can exploit that existing knowledge by a process known as transfer learning, basically taking the learning from those models and applying it to our own new problems. Using the pre-trained models as a starting point rather than starting from some random initialization gives us a leg up in our own task. It probably doesn't solve the task. We will still have to do some additional training. We may have to fine-tune the features that have been learnt by the pre-trained model, but it gives us a good starting point. We can keep or discard as much of the pre-trained model as we like. We may decide that we only want the first couple of layers, which we think will have learnt extremely universal image processing filters like Gabor filters and edge detectors, or we may want to keep the full depth, all the convolutional layers, all the way up to the most detailed cat detectors in the deepest layers. A very common strategy is to keep most or all of the convolutional layers and just discard the layers that come after it that actually do the task that the model was originally trained for, such as ImageNet classification, and then stick on our own heads onto the model, our own layers that do some other task, and just train those on our own data. Layers for which we are using pre-trained weights as a starting point can either be trained further using our own data to adjust the weights to be better suited to our task, or they can be frozen, which means that you just leave them as they are. Quite commonly, people will want to leave some of the earlier layers frozen, just leave them as they are, and then retrain or fine-tune, as it's called, the upper layers to be a bit better suited to your task. So we've covered quite a lot of ground in our 2 weeks on neural networks. Now, a decade ago, and perhaps even more recently, much of this stuff would have been pretty cutting edge. It would have been at the frontiers of research in deep learning. If you wanted to put any of this into practice at that time, you would have had to do it all pretty much yourself by hand, implementing everything from the ground up. You'd have been wrestling with numerical computing issues and libraries and graphics card drivers and whatever. That is definitely no longer the case. We're at a point now where at least much of the basics in deep learning technology have been more or less commodified so that they're readily available to end users. Many of the structures and algorithms underlying deep learning are extremely well understood by now, with standards and conventions as to how things are done. In the language of operation graphs and layers and flows of activations and gradients, many of the components of the models are explicitly and by design conceptualized as building blocks, local units that only need to know about their own state and operations and only need to worry about their immediate connections. And these are things that we can put together like Lego blocks. Software development frameworks for deep learning can and do provide this functionality more or less off the peg. Doing things with these frameworks is a lot easier than doing it by hand, and also likely to be done better because people at Google who make TensorFlow or whatever are paid to spend many, many hours optimizing this code, and you and me are not. A core part of these kinds of deep learning frameworks is a library of layers which implement all of the kind of components that we've talked about in these lectures. There are layers for simple linear weighted sums, or for convolutions, and for recurrent units like LSTMs. There'll be layers for different kinds of activation, layers for regularizing operations like dropout. These frameworks will also provide you with all of the standard optimization algorithms and with all of the common loss functions and activation functions. And they will provide utilities for doing things like data management and converting images into standard formats and all of that kind of thing. Furthermore, they'll usually provide standard implementation of a number of well-known and successful models with utilities for loading their pre-trained weights as a starting point for transfer learning and fine-tuning, for example. And perhaps most importantly, they typically will provide you with hardware support. So computer graphics has made enormous strides in the recent decades and is driven a lot by consumer demand for things like computer games. Graphics is mostly linear algebra. And so if you want to make Doom run really fast, what you need to do is have highly optimized vector and matrix operations and be able to run lots of them in parallel. Graphics cards manufacturers have spent an awful lot of time and energy and money being able to do just this. But it turns out that this is useful for plenty of other things as well as graphics. Lots of other kinds of activity depend heavily on linear algebra, and machine learning is obviously a case in point. GPU manufacturers knew that this was the case, noticed that there was demand, and started providing driver support and programming interfaces for using their hardware for non-graphical, more general computation tasks. NVIDIA's CUDA is the most well-known and most widely used of these. But coding to CUDA isn't much fun, and it's a big distraction from knuckling down to the actual neural net activities that you really want to do. An advantage of using a deep learning framework, of having this kit of parts that you can plug together to make your neural networks out of, is that it becomes somebody else's problem to figure out how to make those parts run on a Titan X card or whatever. Popular frameworks like TensorFlow and PyTorch provide GPU support more or less for free. There are a few things that you need to do, some minor tweaks to tell it that you actually want to use the graphics card, but for the rest of it, it just sort of works. The vast bulk of your code for building models and training them and testing them will work seamlessly on GPU or on CPU without you even having to think about it. A big part of how they do this is by operating at a slightly abstracted level. So when you wrote your multi-layer perceptron using NumPy, you would have written functions that were actual functions, and you would have had arrays of data that were actual arrays of data. When you write this sort of thing in TensorFlow or PyTorch, it will often look very similar. You will have things that look like functions, you will have things that look like arrays, but in many cases, those things, those apparent arrays and apparent functions, will actually be placeholder objects known as tensors. These tensors capture what you're doing or what you want to do as graphs of operations on containers of data, but the actual functions and the actual data may be deferred to some other implementation, say off on your GPU. One of the consequences of this is that you often can't exactly apply, say, NumPy functions to tensor objects because the data isn't necessarily there. In the case of Python, the two dominant deep learning frameworks these days are TensorFlow with its associated higher level interface library Keras and PyTorch. So your choice of framework is the sort of thing that inspires enormous theological fervour amongst techies, but I'm not going to get into any kind of holy war here. Both frameworks are highly developed, very functional, they've got loads of features, they both will more or less do everything that you want. In the early days, there were significant differences between them. They had different emphases and the way that you used them was different. In particular, TensorFlow required you to build and compile your model completely before you could use it at all. These kind of differences have mostly disappeared over time, and the capabilities of both frameworks are now very similar. I'm not going to suggest you should use one or the other in particular. You should use whichever you have more affinity with, or in particular, whichever the people are using whose work you want to borrow and steal. You will see some simple examples using PyTorch in the week's lab exercises. So that's pretty much it for our discussion of neural networks. Pretty much everything we've discussed over the last 2 weeks is readily available in TensorFlow and PyTorch, and it's pretty easy to put it to use. So if you want to go and try anything, please do. For most problems, the difficulty is not finding the one solution, it's that there are multiple solutions and you have a problem of narrowing it down to the one that actually suits you best. The field is constantly expanding and it can be difficult to keep up, but the basic techniques that we've discussed will get you a really long way. We'll come back to touch on a few more topics related to neural networks and deep learning towards the last 2 weeks of the module, but for the time being, that's it for supervised learning. Next week, we'll start with an introduction to unsupervised learning.